She's on the bench. 1.3, 12 basic functions. Nothing new, you know.
No.
All right, so the way this section typically works is that there's usually a question on the quiz/test that says something about you need to write the 12 basic functions. Okay, so when you do that, you have a couple options. I say that. You basically need to write the function as it's written on there. So you would need to write like f of x is equal to x. F of x is equal to the square root of x. If you want to write the names of the functions, that's fine, but that's what I'm looking for. So basically, you need to memorize those 12. So I'm telling you that now. I don't necessarily always require you to write all 12. Sometimes I'll say write 6 and everyone after that is an extra half a point or something like that. So like give you a little bit of extra credit and some leeway because like let's be real, the odds of you remembering all 12 the first time through, pretty slim. So, but then the way the rest of this section works is basically there'll be questions like what we're about to go through with the examples. And it'll say something like which 3 functions do blah 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 and whatever the thing is. So like it might be like have a domain from negative infinity to infinity or something like that, and you have to answer those and use the questions that are there. But the good news is I only use the ones out of the book and the ones that I do in the notes. So I may not assign you every odd problem, but every one in the book is fair game, so it would be good to do them all even if I don't assign them all. So the first ones we're going to look at are domain problems. So, which 3 functions from the graph do not have a domain of all real numbers? So when you go back and look at the graphs, so it might be beneficial for you to either like go to the copy machine and make a copy of the 12 graphs just to have like it so you can like refer back to it if you don't do your homework on a separate piece of paper. But like to go back to, so a domain of all real numbers means it's going all the x values from negative infinity to positive infinity. So this one says do not have a domain of all real numbers. So we're looking for 3 graphs that don't go from negative infinity to infinity, basically. So any ideas on that by looking at the pictures?
Square root function.
Yep, square root is one of them. So y equals the square root of x. And when you're answering these questions, I will take it either written as, you could say the square root function, or you can write y is equal to the square root of x. Or if you prefer f of x is equal to the square root of x, that's fine too. I just usually do y because it's shorter. Another one?
Natural logarithmic.
Yep. Y equals ln of x. And there's one more.
I'll let you take this one,
I have no clue.
Haley. Okay, fine. Reciprocal.
Yep, the reciprocal function. Y equals 1 over x. Okay, because that one has a vertical asymptote at 0 that it doesn't cross, and so 0 is not in the domain. And then the other ones, if you look at the graph, they only go from like 0 to infinity on the natural log and 0 to infinity on the square root. So, all right, still on the domain ones. Let's do another one. Which function has a domain of all real numbers minus basically 0. So 0 is the only number not in the domain. And y isn't 0 in the domain. I unfortunately kind of just told you this one in the last question, but it's fine. So this one, so this is the one that I said has a vertical asymptote at 0, which is y equals 1 over x. And it's because it would be undefined there because of 0 on the bottom. So it has a vertical asymptote at x equals 0 would be y. Or you could write that it's undefined there. That would be another option of what you could put. One more about domain. Which two functions have no negative numbers in the domain? So basically, which ones don't go from negative infinity to 0?
Square root and natural logarithm.
Yep. Y equals the square root of x and y equals ln of x. So those graphs are only on the right-hand side, so that's why. And all 9 other functions, aside from the ones that we listed in the first part, would be a domain of all real numbers if it should ask you that. But usually I don't ask you one where you have to list more than like 4 or 5 of them, but sometimes it happens. All right, the next ones are about continuity. And these aren't out of the homework yet. These are just like examples and stuff that are good. So only 2 of the 12 functions have points of discontinuity. So basically meaning gaps or holes or whatever in it. Are these points in the domain of the function? So I'm more likely to ask you the question, which 2 have points of discontinuity, but this way you've seen it.
What does it mean by if they're in the domain? If there's the domain?
So basically, like, so one of them is going to be 1 over x, and then I'll let y'all try to figure out the other one. So the first one is y equals 1 over x, and so I'm going to write below it the reason, and then I'll do the other one over here. So this one has an infinite discontinuity, which I think we just said if it was continuous or not when we were doing the last section, but it's going to be an infinite discontinuity because of the way the graph goes. But anyways, so we've already said up above that 0 is not in the domain of the function. From this one up here, we see that. But if we take that out, the graph itself is continuous everywhere else because there's no like holes or gaps in it.
Yeah.
So it's continuous on the domain, but it's not continuous at x equals 0 because that's not in the domain because that makes it undefined.
So what is the domain is really what I think I'm asking.
The x values that it takes on.
Okay.
So that one would be from negative infinity to 0, not including union 0 to infinity, and it's not including on the 0 at all because that's where the vertical asymptote is. So anywhere you have an asymptote, it's not going to be in the domain. So with this one, we would say it has an infinite discontinuity. And I'm more so telling you this because if you go on to calculus, then you've at least seen it before. Infinite discontinuity at x equals 0, but it's continuous at every point in the domain. So continuous is basically like it's connected and it keeps going, more or less. So out of the 12, okay, we've already taken 1 away. Any idea what the other one that's got points of discontinuity is? Yep. So y equals int of x Okay, which is also, we've typically called it in the past a piecewise function, but they call it the greatest integer function. Anyways, it's also known as a step function. So this function has what we call jump discontinuity. Because basically there's a line with a hole at the end, and we jump up here and the hole's filled in, and then we have a line, and then there's a hole, and then we jump up here and it's filled in, and then we keep going, and it goes like that. So basically we have a line with a hole, and then we jump up and it's filled. And so it's anyways, that's why they call it jump discontinuity. So this is discontinuous at every integer value of x. So this one is not going to be continuous. And the 3 dots is therefore, just FYI. So this one isn't continuous on the domain because every integer value of x has a discontinuity. So the next thing is boundedness. And so I didn't say this in the last section when we were doing bounded, but I usually abbreviate bounded as BDD just so I don't have to write the whole thing every time because it's really long. So I pretty much just minus the N, I take out all the vowels in one consonant. So, so this one, which 3 of the 12 functions are bounded? Now, when we say bounded, that means above and below. Okay, now if it asks you which ones are bounded above, and it's only above, or are they asking you which ones are bounded below, different question, but this one's asking you which one's bounded, meaning above and below. So it basically gets to a top point and it comes back, and then it gets to a bottom point and it goes back up, and it keeps doing that. Or there could be an asymptote that's keeping it from crossing potentially. As well. So, any idea which ones, or one of the ones that is bounded completely?
Sine.
Yep. Sine of x is one of them. Cosine. And there's one more. Yep. Which is typically the hardest one for people to remember because it's kind of a weird one. But the dotted line that's in the logistic function, it's kind of hard to see, but that's an asymptote, and basically the graph will never cross that, which is why it's bounded above and below. All right, symmetry. Which 3 functions are even? And just so you know, the book is going to say of the 12, pretty much every time. Yeah. Yeah, well, I think they do that so that they're not talking about, every function in the world, but it... So which 3 functions are even? So
Where we would plug in the negative x.
Yeah, basically. So even functions are symmetric with respect to, so WRT is with respect to the y-axis. So that means that if you take it and you flip it over the y-axis, it's going to look exactly the same. So there should be one graph that's very evident that it's even.
The squaring one.
Yeah, the squaring function, because that's a parabola, so it just gets flipped over.
Absolute
Yep, absolute value, because it's a v, does the exact same thing as the square function. So y equals the absolute value of x. And there's one more that might be a little bit less evident potentially.
Cosine.
Yep, cosine. Why is sine not?
I mean,
Because
I
it's
can
not
see
in the
it
middle.
like.
Basically,
that.
yeah. Because if you took it and flipped it over, the low, like the valley, would be on the bottom right. It would need to be on, like, it's not going to look the same if you flip it over. Basically, if you take a mirror on one side and you flip it to the other, it should look the same. And it doesn't. But cosine, because of how it is, it can revolve around the y-axis and look the same.
So we're flipping it this way.
Yep. Yep. Odd functions. Hold on. I don't want to say this wrong. Let me look at the notes from the other day. Pretty sure odd functions are with respect to the x-axis. Let me make sure. Because I know I have that written down. This isn't 1.2. Where did I put 1.2? Who knows? Maybe it's in my head.
I don't know, but I just know that the even functions, I guess they're the ones that look the same. They're
Okay,
symmetric.
well, 1.2. Oh, wait. I found it. It's right here.
I'm trying that. In my head, there's different things spinning on the y-axis, and the only song in my head right now is the "You Spin Me Right Round, Baby."
I honestly think that too.
I think it's kind of entertaining imagining these things spinning around on the y-axis.
A little bit with the song playing in the back of my head.
Well, I don't even have the song, but now I'm imagining them like taking off.
Odd functions are symmetric with respect to the origin. They rotate around the origin. Anyways, it's easier to see that when you actually. That one's the harder one for me. Like the even ones are a lot easier for me to process than the odd ones, because I have to like actually like really sit there and think like what's happening with the other ones. Okay, so I'm gonna, for the moment, skip 2 through 12 in the book, because they give you a graph and basically you're matching it. It's these 12 basic functions, but they are shifted. And so you're trying to match them with the function that's been shifted and whatever. I can't put that on a quiz or a test. We will go over that, but I'm more worried about you knowing these things for the quiz. Like this, so I'm going to go over this. I don't necessarily care if you write the problem like I've been writing, like what I've been writing in black when you do the homework. But what I would say is when you go back to study, it'll be nice if they're there. So I am going to write them for the even ones for you. But a lot of times people find this is one section that they make note cards for, and it's pretty helpful. So, trying to figure out how I want to do this. Okay. Now, 13 through 18 go back to the graphs in 1 through 12, but I'm going to do them a little differently and write what the function would be that meets that requirement, because that's what I'm going to ask you. I'm not going to ask you to match it with a graph, but it'll be the same type of thing. So 14, we have the function whose domain consists of all non-negative real numbers. So what is the only function that the domain is not negative?
I'll let you take this one, Ryan.
There's two.
Yeah, I think
That's because, there are 2 of them.
Maybe.
But they're matching with the graphs from before,
Oh.
and they don't use one of them. But we'll write both of them. And if I only ask you for one and there are 2, if you just put one, as long as that one is right, that's fine. But if you put both and one of them's wrong, as long as one of them's right, I give you the points for it.
Okay.
But you can't, like, write down all 12. I'm not gonna I'm not gonna give you credit for that. But as long as if I'm asking for one and you give me 2 and one of them is wrong, as long as the one is right, that's fine. So so which ones would it be?
Y equals the square root of x, and then y equals ln x.
Yep.
I have a question about the y equals ln x. Is there a vertical asymptote at 0?
Yeah. You can't have 0 inside a logarithm. We just haven't learned that yet.
So would that mean that the domain does not?
Like type in on your calculator ln of 0.
L is 0?
You'll see what I mean. It's gonna tell you there's a domain error. ln should be on the left.
Oh, that looked like an I.
So ln 0, it tells you
Oh, yeah.
domain error, which is y. Oh,
Yeah. So there is one. Because 0 is a non-negative real number.
yeah, technically. So that is why they're doing that. I forgot about that. I forget, well, because, yes, it is not negative, but it's,
But it,
Also not positive.
right.
and it is a real number
Or
though.
anything.
Well, yeah, exactly. So I guess that there really is only
But it's
one,
real.
but.
I don't know.
All non-negative, which would include 0. That's why.
Is this whole chapter this kind of stuff?
This section is, yeah. That's all this section is. The chapter, no, not
Like
necessarily.
with domains and stuff?
Oh, kinda. Not necessarily the entire chapter, though. Probably just mainly these 2 sections. I don't really know what the section after this is, if I'm being honest. Building functions from functions. Oh, no, those are like composite functions and stuff.
I was like, these 2 sections are very hard, and I knew it was on this chapter.
No, it's not. All right. 16. The function that is not a continuous function.
Do you want to do this one, Riley?
Nope.
Greatest integer function.
Yep. Y equals intx. Because the other one, we do have other functions that aren't continuous, but this one is not continuous on the domain, which is why it's not continuous. Like we had, where was it? Up here. This one has a point of discontinuity, but it's continuous on its domain. However, this one was not. So that's why. 18. The 4 functions that are bounded above.
Do you have anything, Riley?
Yeah, cosine.
I concur.
1 second. I'm trying to write them all down because I have the number that they go with of the graph, and I don't want that. So I'm like trying to make sure that if y'all tell me one, I don't have to sit there and look through the 4 and try to figure out what it is. All right, you said cosine?
Yeah.
Okay, yep.
I'm gonna
Yep. And one more.
Square root.
Yep.
Yes.
All right. Now the next ones, they say identify which of the 12 basic functions fit the description given. So this one, you're not trying to match it up with the graph. So anyways, we're not doing anything different. I'm just telling you the instructions changed. All right, 20. The 6 functions that are increasing on their entire domain.
Absolute value.
So increasing on their entire domain means that they're going to be getting bigger as x gets bigger the whole time. So absolute value would be decreasing from negative infinity to 0 and then increasing from 0 to infinity.
So yeah, y equals x.
Yep, y equals x. Because that starts in the bottom left and works up right.
Y equals e to the x.
Yep, y equals e to the x. Same thing, it starts low and goes high.
Y equals x cubed.
Y equals x cubed.
Y equals ln of x.
Y equals ln of x. You got 2 more.
Greatest integer.
Let's go square root.
Yep.
And then logistic.
Yes. Greatest integer isn't because it's every there's those discontinuities at every point and those aren't in the domain. So that's why. Because it looks like it would be,
Yeah.
but that's why it's not.
Does it always increase though, the greatest integer?
I mean, the basic function of it would, but no, not necessarily. They don't have to.
Can it
But
go
we're
up?
only looking at this as the most basic function. Because technically, if we reflected this, it's going to be upside down, and it wouldn't be increasing the whole time. So, that's why.
So with that greatest integer one, would it be possible for it to like go up and down and all that? Or would it just go up? Or
No,
just
the integer function is going to always be going in like a step pattern. We usually call it a step function because it looks like a staircase. But it could be like a staircase going the other way if it was reflected or something. I can't remember what it is that does it, but it can be flipped. All right, 22. The 3 functions with infinitely many local extrema. Now you're probably like, what in the world is that? Basically, this means, so yesterday we did max and mins, okay? And we found a max, and then we would find a min. And I said sometimes they have multiple maxes or multiple mins. So we're looking for functions that basically have a lot of maxes and mins.
Cosine.
and sine.
There's 3 of them. You're probably not going to guess the other one, but
I bet you I will. Ready?
I'm gonna guess greatest integer.
Cubing.
greatest integer.
Dang it.
Ah.
The one time I don't guess that one. I guess that one like 3 different times.
So So
Get it.
it's going to have to, basically it keeps like going and turning around, but because of this one having the filled in holes and the open holes, that's what makes this one have infinitely many local extrema, basically. 24. I'm going to try to get through all of these ones today, and then we'll go from there. 24, the three functions with a range of all real numbers. So basically meaning that they go on the y-axis from negative infinity to positive infinity. So basically they're going all the way from the bottom all the way up to the top.
So let's go with
Cubing.
yes.
Yep. Y equals x cubed is one of them.
The logarithmic one.
Yep. Y equals ln of x.
And then the identity.
Y equals x.
Is there a vertical asymptote on the reciprocal? Not vertical asymptote, but like the horizontal asymptote at y equals 0 for the reciprocal one.
Bigger on bottom, y equals 0. Yes. Hey, I have to think of the clown poem all the time. Like, I can't just do them.
Just doing my homework and
There's also this thing called oblique asymptotes that I swear to you I had never seen until I worked at Bethel High School with the teacher that I was student teaching with. And he starts teaching oblique asymptotes, and I was like, what is that?
Yeah.
Because you can have asymptotes that are actually like a line, like a line with slope.
That sounds scary.
They're different because you can cross those. You technically can sometimes cross other ones too, but anyways. It's weird, I know. But I was like, what is that? I was so confused. He was like, you've never seen this before? I was like, no, I swear to you, I didn't even know this existed.
Exactly.
So, yeah, learn something new every day. All right, 26. We have two more of these. The three functions with end behavior the limit as x approaches negative infinity of f of x is equal to negative infinity. Now, we may have briefly seen this in Algebra 2 when we did end behavior. Okay, but this means as x goes all the way to the left, y is going down.
Okay, so we have.
So as x gets really, really small, basically, because big negative numbers are really small, then we go down on the y. So basically, if you have your coordinate axis, right, your graph should be doing this number.
Identity.
So, yes.
And then the cubing.
Yep, y equals x cubed. And one more.
Natural order.
No, because there's an asymptote at 0. So it doesn't ever cross it. We need it to be going down in the quadrant 3.
Greatest integer.
Yep.
Oof.
I hate that stupid one so much.
Riley's going to start writing that for every single
Every
problem.
single one.
Then she's gonna get it
When
wrong.
you think it should be, it's not. And when you think it shouldn't be, it is. So that one, because the steps keep going down to the left, that's why that one is.
Okay.
You'll get it eventually.
I think that formula just hates me. We love each other.
All right. The last one. The two functions whose graphs are identical except for a horizontal shift.
well, I guess I'll take this one. I don't know if Riley understands what that means.
I got this. You ready?
So-
Fine.
Basically, the graphs look the exact same thing. You just need to shift one of them over.
Sine.
And
cosine.
I was like, there's two of them, hun. So y equals sine x and y equals cosine x. Gosh,
I honestly wasn't sure you were gonna get that.
this projector drives me insane.
Wasn't it doing that like a week ago?
It's been doing it for a hot minute now. Okay, the last thing that we will not have time to do today, I don't think, because also my clock is like ridiculously slow, I think. No, maybe not.
Just like a minute.
Like 5 seconds. Is it says to graph the function, but we aren't going to do that part. And then answer the following: on what interval is the function increasing and decreasing? Hold on, is that what we're doing? Oh wait, we're doing part B only. Sorry, that is the function odd, even, or neither? And so you can see with the 12 basic functions what they are, which. Actually, there's only 3 of them. Let's do them really fast. Then we don't have to do them tomorrow. 36 is the function f of x is equal to the sine of x plus 5.
You said you want us to graph these?
No, we are not going to graph these. I think I have the answer written down wrong. So just give me 1 second, because I do not want to tell you wrong.
That would be unfortunate.
Okay, no. All right, so we plug in. I did have it right. I just didn't think it was right. So we plug in negative x still for x. So f of negative x is equal to sine of negative x plus 5. So there are certain trig functions that are even and certain ones that are odd. But this one does not change the whole thing. So this one is going to be neither because of this over here, the plus 5. If the 5 had been in front of this or being multiplied, then it would be odd. I think sine is odd. Pretty sure cosine and its buddy secant are even, and then all the rest are odd trig functions. So this one is going to be neither because of this plus 5, because it doesn't change the whole function. 38. Q of x is equal to e to the x plus 2. I don't know what's happening. So we put in negative x. So q of negative x is equal to e to the negative x plus 2, which we can think of that as as 1 over e to the x plus 2, which does not completely change or keep the same the function. So this one is also going to be neither, because the function looks different now, not just a sign change. And then 40, the last one.
We've got a minute left.
We've got it. This is the last one.
Go on.
G of x equals 4 cosine of x. So we plug in negative x. So we have 4 cosine of negative x. So this one, because it's being multiplied, cosine's an even function, we're going to call it even. All right, the problems, just so that you have them, you're going to have time tomorrow. Now, we are quizzing on Friday, so if you have questions, that way you can ask tomorrow, but you do not have to, you'll have time tomorrow to work on them, but.
Because aren't these ones and 1.2 both due Friday? Or is 1.2 due tomorrow?
I mean, I'll just let it be due Friday. I don't really care, but all right. So we're gonna do 13 through 27 odd, or well, yeah, 13 through 27 odd, and then I'm not gonna have you do the even, odd, and either ones right now. We might look at those more later, but I just wanted you to see them. So, anyways, there's that.
I have questions about all